Good morning, calculus class. This is my first Zoom video, so hopefully everything will go well. But in it, I intend to go over the theory of average values. So let me switch you over to my iPad so you can see me right. Okay, I think I'm back recording. Let me start writing on my iPad. So remember, if we're trying to find the average value of something, you're used to, if you had, say, three numbers, let's say we had the number 3 plus 7 plus 2, and we needed to average those, what we would do is we would add the numbers up. Okay, so we could say that the sum of the values is equal to 3 plus 7 plus 2, which is 12. And then since there were three values, we would take the sum of the values and divide by the number of values. So we would take 12 divided by 3, and we would say that the average of 3, 7, and 2 is 4. Now we can apply this to areas the following way. So let's say that we have a function. Let me start out. Let me get my pen out and change some colors here. Let's do an X and Y axis in black here. So here is just a set of axes, and we're going to put in a function. Let me do that in blue. So the function will do something like that. And we're interested in what this function is doing between an X value of A and an X value of B. So we could think of this in terms of the numbers example that we just had. Let me divide this. It's easier to divide it in half and then into two more halves. So you can see that we have four regions here. We have number them 1, 2, 3, and 4. All right. So if we wanted to, we could find four X values to use. And we could get the average. Let's just say that we use the X values on the left-hand side. We could take that value, this value, this value, and this value. Notice that's all four. So we're using the left side of all four subintervals, and we could add them up. So we would be taking the summation of the function values at each of those X's. And we would be doing that for 4 points. So we would have from I equals 1 to 4, and we would put that over 4. Okay, so now where are these function values? The X of I's, the first one, that would be X1 right there. This would be X2, X3, and X4. And over here, along the left-hand axis, the y-axis, I should say, would be f of x1 at the bottom, all the way up to f of x4 at the top. So we would have four output values that we would add up and divide by 4 in order to get the average. That would be using a left-hand sum. I could just as easily have taken those four values from the right side. So that would be the right side of interval 1, the right side of interval 2, the right side of interval 3, and the right side of interval 4. So we could have chosen four values from the right side. We can see the average of those would clearly be a bit higher, but there's no reason that we should favor the left or the right. We could just also, let me do this in a new color. Let's do these in purple. We could have taken values right in the middle of each subinterval and used midpoint values. So we could have taken four values that way. So if I want to, though, I can expand on this idea to kind of get closer to ideas of calculus and area. So what's up above could have been written as a summation from I equals 1 to 4 of f of x of I over 4. But we could take both the numerator and denominator and multiply those by delta x, where delta x is the width of each interval. And you can see I tried to draw them so that the delta x values would all be the same. Okay. Then we would be dealing with four areas. And since I'm in purple right now, let me just consider four midpoint areas. So we could do Riemann sums, and the tops of the boxes of the rectangles would be somewhere around here. And we could take those 4 areas to get the numerator, and then we could multiply, take the denominator and take 4 delta x steps. Well, if you look at 4 delta x steps, I would go from there to there, which is the right-hand side would be ending at B, and the left-hand side would end at A. So we could have rewritten that as the summation from I equals 1 to 4 of f of xi times delta x, all over b minus a. And b minus a, you look at that, that is the width of the interval. And if we look at the numerator, this is an approximate area using a Riemann sum. So we could approximate the average value of the function by using 4 points in the middle of each subinterval, adding them up, getting areas from each of those by using the point values as height. So that would be height for the output values, and each one of these delta x's would be a width of each subinterval, whereas this width of b minus a is the total width of all of the subintervals. Now, I think you all remember from Riemann sums that we, instead of doing 4 subintervals, we could do 8 subintervals or 16 or 32, and we could keep going. So right now what we have, if we add this up, sorry about the keyboard popping up, is we have something that is an approximate area divided by an interval width. So this will give us an approximate average value for the function. If we wanted to turn the approximation into an exact amount, this is where calculus comes in, and with Riemann sums, I could turn around and say, instead of doing the interval from 1 to 4, let's say that the average value, and we'll call that the average value of f, is the limit as n goes to infinity of the summation from I equals 1 to n of f of x of I delta x, all over b minus a. Now, the numerator of this, I just highlight that. Okay, the numerator of this is our definition, how we started out giving the definition of a definite integral. Okay, so if we have Riemann sums with an infinite number of slices, then where the limit of n is approaching infinity, that would be equivalent to the definite integral. So we can rewrite this, that f average is equal to, the numerator would be the integral from a to b of f of x dx all over b minus a. Okay, so we would be taking the actual area underneath of the curve and dividing it by the width, and this will give us the average value that we're looking for. So going back to the beginning, we had started with assuming we had 4 subintervals, but as we go to an infinite number of subintervals, our summation becomes an integration, and we end up with a formula for average value. Now, another way to think of this is to think of it geometrically. So if we want to look at all of this geometrically, we could draw another set of axes, put in a function. We're going to look at this from x equals a out to x equals b. And if we were to complete the top with a line that looks like this, it looks like that line that I just drew was a little bit high. So let me get rid of that line. Whoops, put the function back in. I'll put in a simpler function actually. And let's consider where we should put a line in here so that the area under the rectangle matches the area under the curve. And that looks reasonably good. So you can see that the area over here is compensated for by the area over there. Those two regions are about equal to each other. So the height of this line we'll call F average. Okay, and if we consider the area of under the line, which will be a rectangle, oops, see in there, that should equal the area under the curve. And when I say area under the curve, I mean between the curve and the x-axis. Now, we can write these out. The area under the line would be F average, that's how tall it is, times the quantity b minus a, that's how wide it is. The area under the curve, using calculus, is the integral from a to b of f of x with respect to x. And so we can see if we want to solve for f average, this is going to give us exactly what we had before, the integral from a to b of f of x dx divided by the quantity b minus a. And so this gives us exactly the formula that we had before, but we can interpret that as the average value of a function is the height that will give us an area under the rectangle, which is equal to the area under a curve on the same interval. Okay, let me stop the video now.